Yes, so today we are going to be going over how to run a Ansys multi-physics simulation, fluid simulation on the workbench. So first you want to go down to Start, then go to Ansys Multi-Physics 2023 R2, and then scroll down until you find Workbench 2023, and then click on that. And this is going to take about a minute to load. Before we run this, we will need a geometry file, which is either saved as an IGES or as a step file. I've already downloaded that, and how to save those files is gone over in my SolidWorks videos. On your SolidWorks, you can just go to any open shape and then go File, Save As, and then change this to either a step or an IGES file. So the fluid simulation type we'll be using is a fluid flow CFX. So double click on that, then double click, or before you double click on the geometry, right click it and make sure it's set to new design model or geometry, and then open that. This is going to take a minute to load. The first step is to go to File, Import External Geometry File, and navigate to where you have saved your file. Then open the file and generate. Once you have done it, for detail analyses, you will want to select all the different faces on your one. To move it around, you hold down the cursor, and to select a new face, you hold Control down and click. After you've done that, right-click and go to Name Selection, Apply Geometry. There should be 4 faces, and name it to Airfoil Walls. And then generate that. Then go to Tools, Enclosure, and generate that. As you can see, the box created around our airfoil is fairly large, so we're going to shrink that down by changing all of these parameters to 0.3 meters. These just vary how much in the X, Y, and Z it is spaced, at least from each of your edges. Once you've generated the enclosure, you can go to Create Boolean, change the operation to Subtract, set the target body to click on anywhere in the enclosure, and then apply the geometry. For tool body, click over the airfoil, click this second rectangle here. This basically selects one layer below the top layer of what you clicked, and then apply the geometry. Double check that it's the right one by doing that, and then generate the Boolean. Oh, sorry, I didn't forgot to apply the geometry. I'm going to delete that and start over. Create Boolean, target the enclosure, and tool body is the airfoil. After you're done, there should be one part and one body, which is the solid enclosure. And you should have an airfoil walls surfaces generated. Click the save and name this. Name your project file. Once that's successful, you can close your geometry file. After you've done that, refresh your mesh. The arrow symbol here is used to indicate the mesh needs to be refreshed, so it knows what has been updated in your geometry before you can load the mesh editor. And once you see the lightning icon, you can edit. Right-click and then edit. going to take a while to load. But once it is, and you see this rectangle here, you can generate your mesh. This little green lightning icon here means that it's currently meshing. You want your physics preferences here to be set to CFD and CFX. For larger element designs, you will want to set your element order to quadratic and change other settings. And once you can see all these triangles here, you've created your thing successfully. Now we want to create our name selections for the inlet and outlet. The negative X direction was where our front of the airfoil was, so we're going to click that and name the selection the inlet. We're going to maneuver to the back, select this face, and name it outlet. We will then select these 4 boxes that go around the airfoil. Create a name selection and call them fluid walls. You can click down to see that all 4 of these have successfully generated. Yes, you can click on the wireframe display to more clearly see what the front and back edges of everything is. After you've done that, save inside the mesh editor and exit out. After this, you're going to have to update the mesh part here by right-clicking over mesh and selecting update, both of which correspond to the yellow lightning icon. Now we can refresh the setup and load it by double-clicking it. The first step is to insert a boundary. We're going to name it inlet. Make sure this location set to inlet, and set the normal speed equal to the velocity of your airplane. If you want the air to flow in at an angle, you can select Cartesian velocity coordinates and set that equal to the direction you want your simulated wind to be going at. This is going to correspond to the approaching velocity of your plane. And so if we apply that, we can see the arrows are flowing towards the airfoil the way we want them to. Then we're going to insert boundary again, naming it outlet, location outlet, boundary details. The relative pressure is set to 0 and a subsonic option. You will change that if it is transonic. And the arrows are pointing outwards, which is good. Next, we'll select the boundary and calling it the airfoil boundary. We're going to set this equal to a wall, and the location is the airfoil walls. And the green indicates it's in the right spot. And we want a no slip wall. This is due to the no slip condition in fluid mechanics where fluids directly touching a surface are not moving. We'll set it as a rough wall with a sand grain roughness of 0.007. This is relatively smooth. If you want to have a really rough surface flowing in air, you would increase this value. So we can apply that and okay it. Now we're going to insert another boundary, calling it fluid walls. Set it to wall, and this one will be a free slip wall. Apply and okay. and save that. And then we can exit out of our setup editor. Now we can run our solution. If you want very precise ones, go with double precision or large problem. And start run. Yep, everything's looking good so far. We can see the outer loop iterations are starting. And we have our variable values and time steps. The usual range is 0 to 20. If you want a longer simulation, for example, one where you do not end up in a steady state, you may want to increase these values. Yes. So here we can see the lines representing the mass, momentum, and the momentum in the other directions. These values typically spike up or down in mass's case, and then gradually decrease. You can see here they're on small orders of magnitude. What this represents is the approaching of a steady state. So each of these will gradually, with time, vary less and less, meaning that eventually the system can be treated as a steady state when it has, like, say, only 1 times 10 to the negative 4th variation in each of its values between each second to the next. So basically the lines gradually stabilize at a roughly constant value. You can also select the turbulence option and see how that changes over time. This is typically the longest waiting step in the process. You'll know it's working correctly because most of the errors usually occur right after you click run. Once you see it's gotten correctly to, like, say, time step 2, you can probably take a break and come back to the screen several minutes later, like, say, 4 minutes if you're in a rush. As we can see here, the fluid flow simulation has successfully run. If we scroll through this bar here, we can see various quantities like the Reynolds number, density, dynamic viscosity, velocity, and we can also see these important values. Anyway, most of the information is in the next step. So there's no real save button on here. Once this closes, you can see that it runs. "23 outer loop iterations. Now we can go to the results. Here is where we seek to create visual representations of our data. One of the most useful of these is the contours. So we want to set our contours number to a high value. For this variable, we're going with pressure, global range, and for the moment, we just want it on our airfoil boundary. And as we can see here, the pressure is very high right at the tip of the wing. It is also high where the flap starts and is very low on the top side where the flap starts. And generally, the pressure is negative above the wing and very high positive below the wing, generating positive lift. To create a second contour, you just click on the box again and create another one with a new name. Change the variable to turbulence eddy frequency, go with 100 contours. We got to make our pressure contour invisible and then apply our turbulence one. Here we can see that turbulence frequency occurs mainly at the very back of the wing, which is what we'd expect. If it was occurring more on the wing, we would want to change the properties of how we were running it, or how our flight characteristics were going to be. We're also going to generate a turbulence energy contour set to turbulence kinetic energy, 100 contours. Oh, this number basically controls how detailed it's going to look. And here we can see that the high generation is right at the tips here, these corners, where the error is going to slip over. So it's got basically the gap from the flap is adding energy, as well as the spiraling motion that we're going to see later. So they're interacting with each other and generating a lot of turbulence energy. So the higher in order this number, the more energy we're basically losing to turbulence. And you can also see the turbulence starts to generate below the wing at the flap. We can also try generating our velocity contours. So for velocity, I usually recommend using the vectors or streamlines option. But we're going to create it here on the airfoil boundary again. Set the range to local. Yeah, that didn't work. Okay, vector. So first we're going to create a vector and set it to the default domain as location over all domains, vertex sampling, factor, all these. And here we can really start to see the spiral motion that generates at the wingtips. So since there is a high pressure below the wing and a low pressure above the wing, the air wants to basically equalize the pressure. So the high pressure tries to move around and get to the low pressure area. This is what produces this spiraling motion you can see in the arrows. And it's very extreme here, right at this point where the flap is separating. And so again, this creates a loss in energy. And as you can see, there's kind of some missing arrows in this section. So this represents where that turbulence is, because the air creates a gap and it wants to fill it. As we can see, this spiral effect seems to mostly stop by this point, and even at this point, the arrow is at very low magnitude pointing downwards. And this represents simply a small fraction of our wing, so we can judge that it has a high enough aspect ratio for this simulation. We can also generally see that far away from the wing, the velocity remains relatively constant. You can also see right where it confronts the tip of the airfoil, it slows down ever so slightly. And you can also see the trend that the velocity is higher by being more orange above the wing and a lower pressure, more green and blue below the wing. We're going to create another vector and calling it a 2D. The 2, V2. Actually, streamline. Yeah, so we're going to do a similar process with streamlines starting from the inlet. Change points to 2500, set the variable to velocity. And here you can see a similar pattern here with orange lines going above the airfoil and bluer lines curving below it. I'm going to increase the resolution by adding more lines. And you can generally see that same path and a similar spiraling motion here with the 3D streamlines. You can also set it to skew as face center. And this generates more of the lines near the center. But I'm going to go back to the equally spaced one and save that. Make it invisible and generate another streamline, calling this one a 2D streamline. You can't use numbers for the first character. And so setting that to a surface streamline, setting the surface to the airfoil boundary, number of points 2500, equally spaced. Apply. It takes a second to load. Yes, and here we can see a very detailed image of how the velocity profile changes on the wing with a very slow position at the front, an increase on the top, and a massive increase at the flaps. And its opposite is basically reflected on the underside. You can also see how as it approaches the tips, the velocity changes less extreme. From blue to orange, it's only blue to yellow. This is due to the previously mentioned effect of the air curving onto the bottom, and so that decreases the lift generation by decreasing the velocity change. Yes, and if we lower the resolution, you can see the individual streamlines and how they behave. The final one we can do is a volume rendering. For this one, I'm just going to go with pressure, setting the transparency to 0.95 and the resolution to 200 and applying that. It's taking a while to load. So I think this is most easily viewed perpendicular. And so here you can see the high pressure generations at the front, where the flap starts on the bottom side and at the very end of the flap. And similarly, low changes at the airfoil at the start of the flap on the top side. And with this color change, you can gradually see how the effect becomes less extreme as you move away from the airfoil, to the point where it's basically fully equalized and starting to be constant at the very edges of the box. You can also analyze similar properties with eddy viscosity, pressure, and temperature. However, we're not using temperature in this simulation. The other important part to an Ansys report is the report viewer, especially the user data. So we want to make that visible. And so you may have to refresh the page a few times and just click around until the user data is generated. Refresh. Gonna make visible the solution report, refresh. And here we can see the mass flow at various points, which you may find useful. However, in DBF and R analysis tools, these are the main forces we will be looking at, the pressure forces and the viscous forces. These would be good for, like, the viscous forces are good for analyzing, say, how much force is basically dragging along the sort of plastic monocoat that is used for wing coverings. And the pressure forces is primarily for, like, lift and drag. So for your wing lift generation, you would want to look at the total forces in X, Y, and Z. As you can see on our model, a positive Y force is going upwards, so that would correspond to lift, and a positive X is drag. So here you can see the drag force and the lift force. So these are the two main forces we are going to be interested in. And so that is all I have for the Ansys fluid simulation.